Hi everyone, welcome back to another glorious activity video. So this week our topic was correlations and regressions. So I've posted the instructions as well as your answer sheet onto Beachboard. So go ahead and pull those up if you haven't done so already. For our first spreadsheet, we're going to be looking at different fitness testing, something kind of similar that we've done before. And actually, I think back in the first activity, we started to hint at correlations. We just didn't look into relationships as deeply as we are this week. So the goal for this spreadsheet is to understand how to calculate the Pearson's correlation coefficient R. And we're going to be using both Excel and SPSS to find this. We're going to do Excel first. So our scenario is we've collected data on different fitness tests from a random sample of high school students. We're going to assume that this sample is normally distributed so that we can run our correlation and accept the results from that correlation. We're interested in investigating if any of the tests have statistically significant relationships with one another. And we're going to use this using the correlation function. Okay. Now this correlation function, I want to highlight that it only calculates the Pearson's correlation coefficient R, which is going to be the relationship between two variables. So if you're doing a multiple correlation, you can make a correlation coefficient R, but you're not going to be able to combine all of the variables. You can only compare two variables at a time. Okay, so we're going to start out by making a correlation matrix. So you can go ahead and copy your titles, and I'm just going to paste them over here. And when we make the matrix, we have to have our labels on the top as well as on the side. So a quick way that you can do this is copy these labels, and then in this box you're going to right click, go to paste special again, and then you're going to click transpose. What this does is it takes the order from left to right and switches it from up to down or top to bottom. Okay. And then I'll just expand those, and then my thing with formatting. So row height is 31. I'm just going to change this because I don't like it. Okay, much better. All right, so we have our labels on this side of our matrix and labels on the top side of our matrix. Why didn't you fix? That was rude. Okay, so what we're going to do is we're going to use our correlation equation. So we type correl, and then you can see within the equations it's asking for array 1 and array 2. Array is just referring to the range of data for a given variable, right? So we're comparing the range of data for variable 1 to the range of data for variable 2. In this case, we're looking at mass related to mass. So our array for variable 1 is going to be all of the mass data. We put a comma, and then array of variable 2 is going to be, again, the mass data. Now there is a shortcut that you guys can use to highlight this entire column. So if you click on the first box, you press Shift, Command, or Control, and the down arrow, it will highlight the entire column for you. Okay. So we press Enter, and then for this area, what I'm going to do is have you guys report to the second decimal place. Actually, hold on. Do I want that? If I go to answer sheet, just kidding. You're going to do to the third decimal place. I did specify. I forgot. Okay. So we're going to increase decimals to 3. With this, we would expect a perfect positive correlation because all of these are the same numbers, right? And we should see this trend on a diagonal all the way down to where we're comparing 500 meter swim time with 500 meter swim time. So I'm going to copy and paste this, and then all we have to do is adjust the boxes. Whoops. Okay, so same thing with pull-ups. So let's say that you completed all of these calculations. They should reflect, right, correlations using the same range for the given variable that you're comparing. So what I'm going to do is, because these represent our perfect correlations, I'm going to make all of these yellow. Okay. Now we're going to calculate our correlation coefficients for each of the comparisons, right, between variables, or these would be our bivariate correlations within our multiple or multivariate correlation. Okay, so if I want to look at the relationship between mass and push-ups, doesn't really matter which array I put in first. So I'm going to put in mass first since it's the first column. Okay, and then comma, and then you enter the push-up data. Okay. So if we double click this, we know that as we copy this downwards, what's going to happen is our column reference will change, but the reference of mass should not change. Okay, so that's something to keep in mind. As we copy this downwards, we should see that mass stays the same, right? And then pull-ups will be the category we're looking at. Same thing here, mass stays the same. Now it's shuttle run. The other way we could have done this is to put put a dollar sign in front of the row references. Okay. Additionally, if you wanted to put a dollar sign in front of the row references for the secondary variable, right, this would have also worked. So if you take that approach, all you have to do is, drag the boxes over, which in hindsight, I should have done that in the first place, but here we are. Either way you decide to do it, you should just make sure that your mass is compared to the appropriate variable that's indicated in the label column on the left. Okay. And then basically we're just going to do this for each variable pair until we get the completed matrix. So go ahead and work on that, and then you can compare your answers to what I've got. All right, so your table should look relatively similar to mine. And then something to note, which we brought up in lecture, is that the top of the matrix is going to be identical to the bottom side of the matrix. So really, when you make a matrix, all we care about is the bottom portion, right? Because the top is going to reflect the same correlation coefficients as the bottom, okay? So within this matrix, on your answer sheet, You're going to indicate how many pairs of variables have correlations between either 0.4 and 0.6 or negative 0.4 and negative 0.6. Okay, so these are representing basically pairs in moderate strengths, right? So you're adding up how many are between this plus however are between these two values. Okay. Also, with this correlation matrix, you're going to be able to find what R is for mass and pull-ups, describe the strength and direction of what this value you get means, and then kind of put that into words on what that correlation, strength, and direction indicates about the two variables. Okay. Next, we're going to make some scatter plots. Okay, so we're going to have a scatter plot between push-ups and pull-ups, swim time for 500 meter and 25 meter, and then another scatter plot between mass and push-ups. So if you guys remember, when you highlight your data to put into a scatter plot, the x variable has to be on the left, the y variable needs to be on the right. So if we're doing push-ups and pull-ups, I've identified which variable is x, which one is y. Push-ups and pull-ups, we would say these two columns, right? Or you can highlight the data for those two columns there, right? We're going to insert scatter plot, just the regular one here. And I don't know why, again, but the graphs end up extremely small. So you might have to do some reformatting so that the numbers show up bigger. Just remember when you copy and paste into Word, the font will still be large. Okay, so I'm just going to blow up the font size on my graph so that it's a little bit easier to see. Okay, so for your chart title, this is going to be push-ups versus pull-ups. Okay, we need X and Y axes labels. Okay, so I'll let you guys insert those, but just know they need to exist. Okay, and then on your instructions, I've told you what to put as your axis bounds, and this one's going to be 5 to 30. The reason this is you see all this empty space over here and this empty space over here. It's kind of dead space and unnecessary, and it kind of makes this portion look a little bit different than it actually does. So to change this, you're going to double click on the x-axis, and then you see a minimum and a maximum bound. We're going to change this to 5 and 30. Okay, increases by 5 is still okay, so you don't have to change that portion. But now you can see this is blown up a little bit more. It looks a little bit cleaner. Okay, so that's kind of working with this section. In addition, we're also going to add a line of best fit. Okay, so the way that this is going to work is within your graph, so you click anywhere on your graph, you're going to go to add chart elements, and you're going to go to trend line. We're going to add a linear trend line since we're working with linear correlations and linear regressions this week. Okay, and then you'll notice the trend line pops in. What I'm going to do is change the color. I think it's a little bit easier to see. I'm also going to change the width just so it shows up nicer. Okay. In addition, later in our graphing sections, if you double click on the trend line, you're also able to display the equation of the line on the chart as well as the r-squared value on the chart. For these scatter plots, you're only worried about getting the trend line, so no equation, no r-squared is required. Just make sure you have the correct data plotted, the correct axis bounds for the x-axis that are specified in the instructions, the axes titles, as well as a chart title describing the relationship between the variables you are plotting. Since this is not new information, I'm going to have you guys do the other two graphs on your own. Okay, so that's between swim times as well as mass and push-ups. Okay, again, make sure the organization of your variables matches the general setup where your x variable is on the left of the right variable, which is your y, right? So it's x, y orientation. Okay. When we run this in SPSS, okay, we're going to run what's known as a bivariate correlation. Okay, and basically this is a really nice method to use in SPSS. So we're just going to highlight all of the data and we're going to paste it with variable names in SPSS. The default for the variables should be scale. Why didn't you work? Oh, maybe it's because I didn't copy. That's dumb. All right. So paste with variable names. It should be scale, right, indicated by the little ruler here. And that's because we are working with ratio data, right? Doesn't matter what we're regarding as our independent variable versus our dependent variable. They're all ratio data. So I'm going to close this for a second so we have a little bit more space to work with. So you'll see when we want to run a bivariate correlation, we're going to go to Analyze, which is where we find all of the tests we're going to be running. From there, we go to Correlation, okay, which is, or Correlate, same thing, right? And then Bivariate, okay. Once we click on that, we should have some options pop up. And this is kind of what these are going to be referring to. You want to make sure you're calculating Pearson's correlation coefficient and that you have a two-tailed test. Remember, we said that for this class, we're always going to be looking at two-tailed tests. Okay, we're going to insert all of the variables into our variable box. And then under options, okay, it says check the box to include the calculation of mean and standard deviation. Okay, so you're just going to check that box, press OK, and then flag significant correlations. This is just going to indicate it by an asterisk next to your significant pairs. Okay, so you just press OK, and then we end up getting our output. So I'm going to call this one fitness testing so that I know which spreadsheet it goes to. And then you can see we have the means and standard deviations calculated for each of our variables. And then look at this, right? All that work that you guys just did in Excel, SPSS did very, very quickly. Okay. In addition, SPSS will also calculate the significance. So you can see down here at the bottom, if you have a double asterisk, that means your correlation is significant at the 0.01 level, meaning that the two tails combined will give you an area equal to 0.01, which is also associated with a 99% level of confidence. And then a single asterisk will give you a significant relationship with a p-value set at, or an alpha value set at 0.05. Again, it's two-tailed, so 0.05 is the sum of the areas in the two tails. Okay, so when you read this, right, if we're looking at mass compared to mass, the Pearson's correlation coefficient is going to be that top number. Okay, so same thing if we're looking at shuttle run versus pull-ups. I'm tracking right here. Okay, so correlation coefficient would be 0.015. From there, we can say this relationship has this level of significance, right? In this case, it's not significant. And then we can see how many values were inserted. So that's what n represents. Okay. What you're mostly concerned about is the Pearson correlation coefficients. Okay. Along with that, you go back to your answer sheet. Okay. You're going to choose a pair of variables that has the strongest positive relationship. You can either take it from the SPSS graph, or you can take it, or correlation matrix, or you can take it from your Excel correlation matrix. Both of them should return relatively similar values, but as always, there's going to be some calculation discrepancies due to rounding errors. Okay. With that pair of variables that you've chosen, what percentage of the relationship is due to chance or influence from other variables? Okay, percentage should be a key word in here. Okay, and there is a specific calculation that I've given you to figure out what that percentage is. Okay. So I'm going to minimize that stuff real quick. You'll copy and paste the 3 graphs into part D, and that should kind of round out the fitness testing example. Okay. We're then going to go to spreadsheet number 2, which is looking at vertical jump, which we're saying is our independent variable, and 100-meter time, which is considered our dependent variable. Okay, so let's look at our data for vertical jump and 100-meter time. Okay. Our goal in this one is to interpret a bivariate regression. Okay, so remember, correlations are looking at relationships, and we can use correlations to build regressions. Regressions create linear equations that help us to predict the values of a given dependent variable, right? So in this case, vertical jump would be our input variable, and 100-meter time would be our predicted variable. Okay, so our scenario is that we've collected these values, right, using a random sample. Again, we're going to assume that all of these data are normally distributed. Okay, and we want to be able to create an equation that accurately predicts, right, trends in future fitness classes for their 100-meter sprint times, or using 100-meter sprint times. Okay, so we're going to make a scatter plot to start. So we already know how to do this. All right, we highlight our data, insert scatter plot. Again, this is stupid. So I'm going to increase my font size for ease of reading for you guys. Again, kind of use common sense and adjust your x-axis appropriately. So I'm going to adjust the y-axis to be between 10 and I think 14 is fine. We'll see how it adjusts. Yeah. Okay. And then I'm going to also adjust the x-axis so we're between 10 and 40. Okay. With this, I want to add a linear trend line, and I'm also going to add the equation and the r-squared values. So again, you guys are going to add in your axes titles and adjust the chart title so that it represents vertical jump versus 100-meter time. And then insert a linear trend line. Again, personal preference, I like to change the color of my trend line. We'll make it 4 points so it's nice and big. And then when you click on this 3-bar option in the format toolbar, you can just click display equation, display r-squared value, and then drag these somewhere onto the chart area where they're not going to be crossing this line here. Okay, so basically when we read this, right, we have a negative slope, right? Y equals mx plus b is our general equation for a bivariate regression. So m, right, or our slope in this case is negative, which makes sense because our line direction is going downwards, indicating that as we increase our jump time, our 100-meter time decreases, okay? And remember, this unit, as we will have talked about in the lecture, is not the R value, which is a very common misconception. This is just saying, right, it's the change in Y over the change in X. So for every single unit of change in vertical jump, we're going to have 0.0891 units of change in 100-meter time, okay? So for every change in X, we get this change in Y, represented by this value, okay? Again, 13.028 is going to represent our Y-intercept, okay? So where this line would cross the Y-axis. And then we get our R-squared value, which is our coefficient of determination / covariance. When you write this, it's represented in a percentage. Okay, so it's telling us the shared variance between variables is about 80.36% or 80.4%. Okay. If you wanted to use this value to find the correlation coefficient, right, we would just take the square root of this value, right? So 0.8036. And that would give us what our actual correlation coefficient is, okay? So this, again, correlation coefficient tells us the strength and direction of a given variable, or relationship between variables. It is important to remember, though, that when you square something, you're going to get a positive number. So when we take the square root of this, it's not necessarily going to reflect positive versus negative. Okay, so that information you directly get from the direction of your slope. So we would have to indicate in this sense our R is going to be a negative 0.896, blah, 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 blah. Okay. So with this information, you guys are going to answer some questions on the answer sheet. Okay, so we're looking at what's the correlation coefficient between two variables, what's the bivariate regression equation you would use, how much of the variation is shared, right, between the two variables. So all of this, parts A through C, you can get from what we just did on the graph, okay? If we're looking at what's the probability that there's no relationship between vertical jump height and 100-meter sprint time, we're going to actually get that from the SPSS procedures. Okay, so we've kind of already done, whoops, wrong highlight. We've done this part. In order to answer that question, we'll have to run the regression through SPSS. Okay. Also using that regression, we're going to be able to find the estimates for part E. Okay. So let's go ahead and jump to that portion. So I'm going to do a new data sheet. There we go. Go ahead and minimize that one. And then going back to our Excel data, I'll just copy this information and paste it with variable names in SPSS. From here, if we're running a linear regression, we do analyze, regression, linear. Okay, so regression, linear. Okay. In this section, let me minimize some of this stuff. You're going to have to indicate, right, what your dependent variable is versus your independent variable. So in this case, I've given you that information where vertical jump is your independent variable, 100-meter time is your dependent variable. Okay. From here, we're just going to keep this as enter. This will change when we have multivariate regressions, but when you're doing a bivariate regression, it's always going to be enter. Okay. Further in here, if you've got your statistics, so we're mainly going to be changing this stuff when we get to multivariate, but for now, you can just keep it the way it is. Make sure this is the default of 95% for your confidence intervals if we were going to calculate those, but you can add in descriptive statistics if you want to. That gives you your mean and standard deviations for each variable. Okay. Within, I think actually statistics is the only one that you would end up messing with. But for now, we're just going to keep things the way that they are. Okay. So in this example, what was this one called? I just want to edit the title. There we go. So we have, I'll put VJ versus 100 meter as my title. Okay, so you can see variables entered, our vertical jump. So this indicates what the, like what variables are going into the equation, which should be our representative of our independent variable, right? The dependent variable should be listed as 100-meter time. Our model summary is going to tell us different characteristics about our model or our equation, if you want to use model and equation synonymously. So this gives us our R value as well as our R squared value. And you can see when we look at our graph here, right? Our R squared value was 0.804, right? Our R squared was 0.804, which matches here, right? And our R value was 0.896, which should also match here. Okay, so that's kind of, you can cross-check to see if you did things correctly. Okay, and then we kind of skip over the ANOVA table. We don't really care about that right now. And then we can look at our coefficients table. This is where you're going to build your regression. So the constant, right, or b sub 0 is representative of our y-intercept, and vertical jump, this b coefficient is representative of the relationship of our two variables. Okay, again, it's not synonymous with the R value, even though sometimes it would be similar, but this is indicating for every change in our dependent variable, or for every change in our x, right, we get this magnitude difference between our variables. All right, so you can also cross-check these two values with the Excel spreadsheet, which I just lost, right? And they should be the same. Okay, so using this information, we can kind of build the same answers for the first three parts, if I remember correctly, right? For these first three parts. Okay, the value shouldn't be too different. Okay, or sorry, parts A through C. Okay, for part D, it says what's the probability there is no relationship between vertical jump height and 100-meter sprint time. Figure out which hypothesis, this is a hint, right? Figure out which hypothesis this is representing within your test. Okay, and then we know probability is represented by P. So this should give you a hint as to how to find this answer. Okay, and like I said, it's going to be in SPSS, or at least it should be. Okay, and from here you should be able to figure out what that p-value is. Okay, So I'm going to go ahead and minimize those. And then we're going to go into our predictions. Okay, so we make equations in order to predict certain values. Whoops, that's the wrong one. Here we go. So if, let's say, I'm just going to label this something. Okay, we're using these values here. Okay, so for our, basically this is representative of our dependent variable or our 100-meter times, right? So we have 10 inches, 21 inches, 29 inches, 40 inches, okay? Whoops, sorry, it's independent variable, the vertical jump. So using vertical jump values, how can we predict our dependent variable? Okay, and we're going to use this equation, right, or the regression equation that we found either in Excel or SPSS to figure out what this predicted dependent variable value should be. So we literally just copy it number for number. 0, 8, 9 is fine. Multiplied by your independent variable x, right? And then you're going to add the y-intercept, or the b sub 0 constant, which is 13.028. Okay, so that should give you your predicted dependent variables copied downwards. Remember the actual b sub 1 as well as the b sub 0 should be constant in this equation. The only thing that's going to be changing is the x input, and then you get your predicted y values. Okay. The last thing we're going to do in this spreadsheet is look at outliers using the interquartile range method. So for this example, what you're going to do is you can use the quartile or percentile functions that we've used in the past to find your interquartile range. Okay, so I guess we can split this up, say Q3, Q1, and the IQR, because those are the first sets of information that you need to find. And then additionally, I'm just going to insert, whoops, too many rows. No, I'm going to insert one row above, right? And then we'll just put our labels of vertical jump and 100-meter time. So you guys know how to find this information, right? Quartile, we're going to use the vertical jump data, and we're looking for quartile 3 in this column. You can copy this over, and that should directly give you the third quartile for 100-meter time. And then we also want the first quartile for the vertical jump data. And same thing for 100-meter. Interquartile range is going to be the difference between our Q3 and Q1. Whoops. Hold on a second. Arrow malfunction. That one minus that one. There we go. Okay, so we get our interquartile range for our two values, and then we can use that interquartile range to find the outliers. Let's call this outliers less than Q1. So this will be the lower bound or the lower end of our distribution. And then we can look for outliers greater than Q3, which would be any variables that are on the upper end of our distribution. Okay, so to calculate this, you can use the equations from our lecture on this topic. We're going to take whatever Q1 is and subtract the interquartile range times 1.5. Okay, so this indicates that any value less than 12.9 would be considered an outlier. Okay. Similarly, for outliers greater on the greater end of our distribution, we take Q3 and then we add the interquartile range times 1.5. Now, the hard part about using this is that how do you sift through a bunch of data to find the values that are outliers? So we can use conditional formatting, where we can use highlighting cells or highlighting rules that correspond with our outlier values. So let's start with our lower bound. So basically choosing this option says any values less than 12.9 is going to highlight in red. So I would be able to see if there are any outliers if they highlight in red, which there don't seem to be any. So then I can also choose greater than and put my 36.5, or additionally I can just click on the cell reference, right? Press OK, and then I can scan to see if any of the values have turned red. If the values don't turn red, then you have no outliers in that particular section. Okay, so I'll let you guys use that method for the 100-meter times to see if you can find any outliers within this distribution of data as well. Okay, and then answers to those or to that portion will be in this area. Okay. Again, you'll copy and paste your scatter plot into part H, and that will complete your questions for part 3 or spreadsheet 3 of the activity, or spreadsheet 2. Okay, moving on to spreadsheet number 3, we start to get a little bit more complicated, where we're working with multiple correlation and regression, but we're primarily going to look at all of this in SPSS. Okay, so first things first, we're going to run a bivariate correlation. This is going to give us our correlation matrix. Okay, and then we'll run 3 different linear regressions to kind of see what type of predictive equations that we end up getting. So going into our Skinfold data, you're just going to copy all of this and stick it into a new spreadsheet in SPSS. So I'll minimize this one, move this one over. Again, you're going to paste with variable names. All of these should be scale. To do our bivariate correlation, remember we go to correlate, bivariate, and then we're going to insert all of our variables in here. Make sure you have Pearson two-tailed, means and standard deviations. Okay, same instructions that we used for our previous example. Okay, this is going to be, I'm going to call this Skinfold correlations. Okay, so within your answer sheet, you'll have some questions, right, with respects to what variable has the strongest correlation to body fat, because in this situation, body fat is going to be our dependent variable slash the value we're trying to predict by making some equation using our independent variables as predictive factors. And then you also want to look at which 2 sites have the strongest correlations to each other. This is not going to include any perfect relationships that we see on this diagonal line, right? So you're going through the matrix to find which R value has the strongest relationship. Okay. Oh my God, so many windows. Okay. In addition, now we're going to find some linear regression equations based on specific examples. So we're going to make a linear regression looking at sum in age, 7 7 sites, right, or all 7 sites in age, as well as a specific ordered trio of abdomen, thigh, and tricep skin fold measurements. So we're going to come back to that. But the way that we're going to start this out, I have the instructions right here. Okay, so we're going to let me not click on a specific cell. Hopefully that doesn't screw things up. We're going to go to regression and linear. Okay. Okay, I was hoping that wasn't going to change. So you can see these two changed to different types of data. They changed to nominal. Make sure that all of your data represents scale, and then we can analyze our regression from there. So remember, the dependent variable is what we're trying to predict. That's going to be body fat. And then in this regression, we're saying we're going to predict body fat using the Skinfolds sum as well as the age. Okay, so sum is an independent variable, age is an independent variable, and we're going to use the enter method, which is our hierarchical regression method where we, the researchers, choose the order that variables go in. Okay. From here, we're going to include the following calculations. So we want our confidence intervals, the R-squared change, as well as descriptive statistics. So model fit and estimates, again, are always going to be highlighted or checked. Keep that the same. Confidence intervals will add in. Again, default is 95%. R-squared change, as well as descriptive statistics, which include your means and standard deviations. Okay. This will make a lot more sense when I press OK. Okay, so I'm going to call this, there we go. I'm going to put sum and age. Okay, so you get your descriptive statistics up here. You get a very small correlation matrix, right, based on the variables that have been inserted. You'll see the variables entered are age and sum. Again, this is an enter method, so we are going to get a single model, right, based on the criteria that we've used. Okay, you'll see within the model, our R value is 0.951, our R-squared value is 0.905. Okay, R-squared change, you'll notice because we have only one model, it's going to be the same as our R-squared value. And this is because if we had model 0, which has no variables in it, when we enter these two variables, they add this degree of R-squared, right? So from there, we can look at our coefficients table, which is going to tell us how to build our regression equation, right? So using the B coefficients, you guys should be able to figure out how to build that equation based off of lecture information as well as some of the stuff we've already gone through in previous spreadsheets. Okay, so I'll let you guys build that. And from here, we can try doing our next linear regression. Okay, so one thing I would recommend is that once you get your equation, you're just going to type it into your answer sheet. Okay, so you'll indicate the R squared, right? And this is combined R squared, so that's going to be indicated by your highest model. In this case, we only have one model, so that one would be like 0.905. And then your equation would go here. Okay. When you write out your equation, make sure you're indicating which B coefficients are going to which X variable. So you could put like X with a subscript of sum, right? Or an X with a subscript of age, but make sure you're indicating which variable goes to which B coefficient. Okay. So with the same data set, we're now going to predict body fat using all 7 individual Skinfold sites as well as age using a forward selection method. So we can go to Analyze, Regression, Linear. We'll take out those two. Okay, so we're doing body fat still as our dependent or predicted variable. And then we're going to use all of our variables except for the sum of the Skinfolds. So those will go into our independent variable list, and we're going to change our method to forward. Okay, statistics, savings, or the settings should have been saved from when you did your first sum and age regression. So they should be set. Just press continue. I think it's a good idea to double check just in case, but they shouldn't change. Okay, we'll call this 7 site and age so we don't get it confused with our other one. Again, you get descriptive statistics. You'll get your correlation matrix. And then this is the part that is important for you guys to kind of visualize how models are built within SPSS. So we start when we're doing a forward selection method, and I explain this a little bit more in the flowchart video that has forward and backward selection and elimination methods. So make sure you check that out if this didn't make sense from the lecture, and especially if it doesn't make sense now. But hopefully with some visualizations it will help, right? So with forward selection, remember we start with no variables in the model. So you can imagine model 0 is going to have 0 variables in it, okay? We then add the variable that has the highest R value or the strongest relationship to body fat, which is our dependent variable, okay? Basically, the highest R is going to relate to the highest R squared or shared variance between our dependent variable and whatever variables are in the model. So obviously, if we're able to predict a higher percentage of that dependent variable, we want the independent variable that contributes to that covariance entered first. So in this case, mid-axillary had the highest R squared value. From there, we just keep adding to our equation based on which variable is going to increase R squared the most next, right? So after mid-axillary, we could say chest increased R squared the most out of the rest of the variables, and then we just keep adding and adding and adding. And you can see this order has been determined such that when we get to model 8 and we had a significant addition to our R squared value, we end up with abdomen being the last variable that's added. So you can see this same order right in our model summary where you can see these little superscripts of A through H, right? This will tell you the order of the variables that are added into the equation, okay? You can see the R squared value is the highest for mid-axillary. Added on to 0 variables, we're going to get the same value, which is similar to the sum and age regression we just looked at, okay? And then this is why I like to include the R squared change. So when we add in chest, right, which is our second model, we're technically adding 0.29 of R squared, or we're adding 12, almost 13% of covariance. So when we add R squared, we have to evaluate, is that addition going to be significant to our prediction equation? That's determined by the sig-F change, right? And sig represents a p-value, basically. So we're using a 95% level of confidence two-tailed test, okay? So if our sig is representing our p-value, when we add in chest to our R-squared value, we get a change of almost 13%, and this just indicates that our p-value is less than 0.001, which basically means that the change was significant, such that we need to keep chest in the equation, right? So we keep doing these comparisons of R-squared. Was that change significant? Add another variable, look at the change in R-squared. Was that addition significant? All the way up until we don't have any more significant changes, which in this case we're adopting model number 8, which includes all of these variables. Okay. From here we can skip the ANOVA table and we go to our coefficients table, right? And this will give us the equation for each model. Again, the models are going to be representative of, I gotta scroll a little bit more, right? Again, this is the order in which they are added. Obviously, the equation that has the highest R-squared value is the model that you want to adopt, because that means you're going to be predicting, right, in this case, almost 92% of body fat, just based off of the variables that have been included in your equation. So, when we build our equation, we're always going to refer to the last model, especially if you're using backward elimination or forward selection, where you get multiple models in your output. You want the one that shows up last, because that's going to give you your highest R-squared value, right? And so then, similarly to our sum and age, right, this is our B coefficient column. So based off of that last model, right, you're going to use your B coefficients to build your regression equation. Okay, so that should make sense. Okay, just to explain, this last table tells you what your excluded variables are. So if you remember, mid-axillary was chosen first in model 1. So if mid-axillary was the only variable that went in based on the variables you are considering for prediction of body fat, all of the other variables will be excluded, right? When we looked at model 2, chest was next, and you can see chest and mid-axillary are missing. So this table is going to be a direct opposite of your model table, basically. Okay, and you can see which predictors have been put in the model, right, based off the area that you're looking at. Okay, so that kind of sums up what this output indicates. So based, again, on this coefficient table in your answer sheet, you're going to write down what the R-squared value is, the shared one, or the combined total, right, for the final equation that you're using. The last method I wanted to show you guys is when you insert in a particular order. So in the first one, we just said enter these two variables, right? And the order that you enter them is specific, right? In the concept, like I put sum before age, but it just enters them at the same time. Okay, we can also use the enter method a slightly different way. So I'm using the same, whoops, that's different. Here we go. Using the same, you can either go from the output or you can go from the data sheet, which should be on data set number 2. Okay, so from either one, I want to do analyze linear regression. Okay, and then I'm going to clear out all of this information. Okay, and now I'm specifically looking at abdomen first. Then I want to see what happens when I add thigh. And then I want to see what happens when I add triceps. So basically I'm saying I'm going to create a model, right, in which I add abdomen first. And then you see this block 1 of 1, right? So abdomen is the first variable entered into the model. I click next. And then I can choose thigh. and then I click next, and then you see block 3 of 3. I'm going to add triceps. Right, so I've specified an order, and I want to see how the model changes based on that order. This is different than when I just inserted sum and age together, and just wanted to see what happens when these go in at the same time. Okay, so this is going to be more of a stepped process that'll turn out in the output similar to when we do a forward regression, except we're selecting how we add variables in. Okay, again, the statistics part should be the same. So in this one, I'm going to call it ABD plus thigh plus try. Same thing, you get descriptive statistics, your correlation matrix, and then you can see model 1, we put abdomen, model 2, thigh, model 3, triceps, which is different from the sum and age where we only got one model, right? When we look at our model summary using this enter method, again, we can see which values or which variables are going to change R squared, right? How much they change R squared by given the specific model that we're looking at, and we can see if that change in R squared was significant or not. We can then build our equation of our regression using our coefficients table. Again, when you are building your equation, you look at the model that gives you the highest R squared value, okay? Because that means you're able to predict a high percentage of your dependent variable using whatever variables have been included in that model. So in this case, again, we always use the bottom model. Okay, so find out what your equation would be for this one. And then we want to use these equations to figure out which one works best in predicting skinfold, which is best in predicting body fat measurements using these skinfold sites that we've collected. Okay, so in this portion, you're going to go to, here's my data sheet. You're going to go to the Skinfold cross-validation. Okay, the first thing I want you to do is copy and paste the body fat values, and this is going to represent actual body fat. Okay, this is an important distinction because this is what actually goes with this given data set. Okay, so remember, cross-validation data sets are used to test the ability of a regression equation to correctly predict actually measured values. Okay, so when we look at this actual body fat, we're going to be comparing it to predicted body fat. So in this case, we're comparing our equations, right? So in the first one, we did sum and age, right? Second one, we did the 7 sites and age. And then the third one, we did abdomen, thigh, and your triceps, right? So each of these, oh dear, I don't know what I just did. So each of these is going to represent different predicted outcomes. Okay, so I'm gonna make that a little bit clearer here. These are your predicted body fat values. Okay, and basically what you can do is say, or we want to know which one works the best, right? So using the equations that you found, you're going to insert or find what the predicted body fat values would be using all of this information, right? So if sum and age are the only 2 variables being considered, you would say this equals whatever the correlation or whatever the B coefficient for sum was times this sum of skinfold value for subject 1 plus the B coefficient for age times the age of subject 1, right? And then you copy that all the way down find out what your predicted what your predicted body fat values would be using the given equation that you found, and then you just repeat that for each of the other two equations. Okay. From here, in order to evaluate, right, how well these actually predicted your body fat, right? I like colors, which doesn't really matter in this case, right? But basically, what you're going to do is you're going to say, how well correlated are these predicted and actual values, right? If you get a correlation of 1, that means the predicted value is exactly the same as the actual value, right? Because if we, let's say in sum and age, we got 15.7 and 18.1 and 10.9, 25.9, and the same values all the way down, that would indicate that this predicted value gives us exactly the same measurement as the actual body fat that was calculated. Okay, so if we use correlations, we can figure out how closely related the predicted values are to the actual values. So in this side of things, right, you can just put the correlation of the actual body fat measurements, comma, and then we'll put in our second array, which is going to be basically N6 to N181, right, or kind of matching this part over here. Okay, within this, I'm going to copy this sideways, so I'm going to freeze my, actually, I'm going to freeze my column references this time. Okay, so as you calculate these, you should get, right, correlation between actual and 7 site, and then your correlation between your actual and your other enter method. So that's going to bother me if it's not right. Okay, so basically whichever equation returns the highest correlation means that you have the closest prediction of the actual body fat. Okay. Using the best equation, right, based on your evaluation, you're going to predict body fat for these 3 individuals based on these skinfold measurements as well as what their age and the sum of those skinfold measurements is. Okay, so that's kind of the last part of this cross-validation area, right? So part D can be answered using the correlation information. Part A of this last number 4, which should correlate to your guys' 4th spreadsheet, is going to be just what your predictions are for each of these 3 people. Okay, now there is specific answers that should come out on this part, given that you picked the correct best equation. So there always is going to be potential for partial credit here if I notice in your spreadsheet that you used the equation you indicated, right, in part D. So for example, let's say you said sum and age was the best predictor, right? And I go into your spreadsheet and I see you used the sum and age equation to, figure out what John, Amanda, and Justine's values are, you'll still get full credit for this part, even though you maybe chose the wrong equation up here. Okay, that's just an example. So just so you guys know, like, this score isn't completely dependent on this part. Okay, but that should give you pretty much enough information on how to complete the activity as a whole. I do think this is kind of the part of the semester where people start to drop off a little bit because it gets a little bit more complicated. So if you have questions, please take a look at this earlier in the week rather than later so you have time to get responses from me, as well as to kind of mess with the activity and try to figure things out on your own, in addition to any help that you get from me. Please make sure you submit your answer sheet as well as your spreadsheet and your SPSS output. Preferably the output should be in Excel format, but PDF is also fine. Okay, and then this is all going to be due in 1 week at 11:59 from the day it's assigned, so 1 week from Monday. Okay. All right, good luck.